elucidate the fact as to how we can essentially retrieve E of t, right. So, the essential idea is the following, right. What we measure, let us take all the possible pulses in the universe. Let us say we take all the possible femtosecond pulses. Okay. Now, depending upon a particular gate, particular type of gate, I can collect all the interferograms, the frog traces for it, and put it in one bucket. And think of this in terms of the phase space, okay, not real space, possible sets of options. Again, it is forensic science. In terms of an analogy, if let us say there is need to figure out maybe an offender or somebody, we have a geometric boundary which is a constraint, and it should, we initially start with, okay, the person of interest could be anybody. It could indeed even be the person investigating this in itself. You do not rule out anybody, right. This is what at least movies would tell us. You do not even want to rule, one investigator should not even rule out the other. But you put a boundary, okay, spatio-temporal boundary on a particular date within a city or within a locality or a neighborhood, the person of interest should have been there. So, all those are possible solutions, but the idea there is to pin down on a much narrower set of people. So, but at least identify the space. Now, with a given constraint, suppose I measure a trace, a spectrogram where most of my data is within a delay, let us say, of plus minus 100 femtoseconds, right, and we have frequency here. The frequency content is, let us say, something like 800 plus minus even 30 nanometers is a lot, let us say 15 nanometers is the region of interest. I am quoting wavelength instead of frequency because we measure wavelengths. Now, this gives us a whole parameter set of space because of the constraint we can impose. Okay. Now, what we then say is, take any typical pulse. Okay. Now, take any E of t, define it by means of an I of t and e to the I phi of t. Okay. Now, take this sort of a pulse and do an iterative process, create the E signal of t out of this. Okay. Now, a set of E signal of t which satisfy this nonlinear constraint, okay, in that this is E signal of t of tau is proportional to E of t minus E of t multiplying the mod square of E of t minus tau. Start with an initial guess, okay, start with some initial guess. From this, now that you know E signal of t, what is the frog trace? The frog trace is merely the Fourier transform of this mod squared. So, start with an initial guess, create the frog trace from it, compare it to the measured frog trace. Okay. If the measured frog trace is over here, compare this frog trace to this, generate an error signal, fine, and then start modifying your E of t and phi of t significantly. Of course, this looks like a really tireless process, but that is what it can be at times. For a well behaved pulse, this will converge much faster. So, do a modification, go, this motivates me to go to a different, this makes me go from pure guess to modification 1, again generate the frog trace and then come back and then go back and then come back. At every step, iteratively generate an error function. The error of the n plus in the n plus 1 step should be smaller than the error in the n step. So long as this happens, it will converge itself to a solution. Then it is a question of computing power and maybe smart algorithms. Of course, it goes without saying, the moment you have a problem like this starts to smell like a case where machine learning starts to smell like machine learning, and indeed people are applying machine learning to do all these retrieval problems. Okay. There are other methods too where this is applied, but for a modern implementation of the frog, okay, indeed machine learning will accelerate the convergence or any retrieval problem for that matter, right. If we do all this right, then voila, this is what we have. We can take a measure of frog trace and retrieve a pulse in the following sense. The sense in which we are retrieving this pulse is essentially the same as that in which we post the problem, that is, we will be able to determine a unique I of t and a unique phi of t pair, exactly the way we were representing these pulses early on. Remember, we said, look, the way we represent a pulse is to use two vertical axes, one time axis. On the vertical axis, intensity, and on the other vertical axis, phase, right. That is what we have been like doing. So, this is of course data courtesy the Kohler-Wilson lab, pretty old, I mean historic, I would say, data. So, we can use frog therefore to unambiguously retrieve ultra short pulses. Of course, this is not the be all and end all of everything. We have some more aspects such as how quickly does this converge and so on and so forth. One needs to be concerned about that. The gating signal, as I said, can be generated out of a second harmonic generation process, okay, instead of the polarization gating which I spoke about earlier. SHG frog is the quickest or the nearest nonlinearity. Beyond linearity is second harmonic. So, therefore, this is the most sensitive version of a frog measurement, right. And SHG traces, depending upon the technique, even a frog trace can be symmetrical about the delay. Earlier what we used was a third order process, which is chi3 process, Kerr effect. Therefore, the frog trace was not symmetric. In this case, it can be symmetric as it is the case for linearly positively and negatively chirped pulses, but this can have an ambiguity in the direction of time, but that is a removable ambiguity. Okay. For complex pulses, again important thing, the second harmonic frog should also reveal the complexity of the pulse even in the map of the of the time frequency map itself. Look at the self phase modulated pulse, the double pulse and the cubic phase pulse. Remember, in all these cases the envelope that is chosen to be plotted here is Gaussian. It is nearly the same, it is a well behaved Gaussian envelope, yet the different spectral profiles, the spectral phase functions phi of omega, at least in the first two cases where the pulse is not double, it is a single, it is just a unimodal temporal distribution, so to say, only phi of omega varies and the frog traces vary. So, as a consequence of this, people essentially have produced and measured pulses with the titanium sapphire laser. Titanium sapphire is one of the go-to gain media for femtosecond lasers, where the pulse essentially has a central wavelength close to 800 nanometers predominantly. Here an optical cycle T is approximately 3 femtoseconds, and in this plot this is a real world measurements, but only up to 1995. We are 20 good, almost good 20 years plus 30 years, yeah, we almost 30 years, 29 years now from this time. Indeed, people had produced in the by 95 already pulses which were kind of like this, right, just 3 optical cycles, which is quite remarkable. But today in published, we can not only, well, that may be a bit of an exaggeration, we can produce waveforms which are very few cycles down to the single cycle limit. Such a pulse like this is a single cycle pulse, that is within the FWHM it contains just one optical cycle, right. There the shape of the field, as we discussed earlier, the C phase, the the zero order phase, the absolute phase and others become really important. The point is, again remember, measurement is the key. If you did not have a technique to measure these pulses out, you did not have measurement, in a way precludes making. To make the pulse, you have to have a way to measure it as well. So, in that sense, measurement is more important, it is more fundamental than making the pulse, right. So, I mean, we have again all kinds of scenarios where pulses of very different types, like in a laser there could be material dispersion, there could be some coherent ringing such as in so called Q switched laser pulses. Typical Q switch ringing happens, especially in the nanosecond. For the femtosecond case, probably that is not the reason, but whatever the case may be, look at the phase profile too, it has step like features and whatever. Now, in all these cases, the measurement reflects features which are similar to that of the, which uniquely maps the state of the pulse as compared to the to what is expected from such a process. Now, frog measurements and SHG frog measurements, such as this work from the Deshmukh group published very early on, even in 99, showed the production of just 4.5 femtosecond pulses, okay, when with this is again with titanium sapphire lasers, 800 nanometer wavelength, this is 2.7 femtoseconds per cycle, cycle time is 2.7 femtoseconds. They essentially measured the tau of the pulse is 4.5 femtoseconds. This is really remarkable. A little bit of dispersion somewhere could have stretched this pulse substantially. Okay. Look at the spectral width of this pulse, it's quite breathtaking, right. 800 nanometer is the spectrum of the pulse, is the central wavelength. Your gain medium essentially would have given them just about this spectral chunk, maybe I am even exaggerating that quite a bit. This spectral band which they were able to cover was actually due to nonlinear optics. A supercontinuum generation step was involved in this case. You can look that up if you wish. Supercontinuum generation becomes an implicit step in realizing these pulses, supercontinuum generation, and then compression with a pair of compression of the linear chirp that is acquired in this process. If time permits, we will discuss the technique in this course, but otherwise I will, for any of you who are curious, I will point you to what it is. Now, how weak a pulse can we do frog with? It has been shown that we can even do frog measurements with picojoule pulses, which is really tiny amount of energy. There is femto natojoule as well. They may be hard to implement using such a technique. Now, for very weak pulses, methods such as spectral interferometry or spider exist, which do not essentially involve nonlinearity to start with. We will look at this in a forthcoming lecture, but we are now also well poised to do what we ultimately set ourselves out to do. That is, I have so far described methods that lead us to unambiguous yet femtosecond pulse measurement, but what about atto, which is what we want to dedicate this course to. That we will learn in the next couple of lectures as we go along. Yeah, I know I have taken a lot of your time today. There was also some intermediate issues. With the screens, we will fix and make that better in the next editions of this course, which is drawing itself towards a natural conclusion. But for now, thanks for being here today, and if you have any further questions, I am still available for some discussion.